Good afternoon all. So this is week 5 problem solving session, Microelectronics device to circuit. I am Arpita Biswas, a PhD scholar from IIT Jodhpur in electrical engineering department. And this is more details about me, that I did my MTech from IIT Jabalpur in micro nanoelectronics, and I did my BTech from Maulana Abul Kalam Azad University of Technology in electronics and communication engineering, and recently I am pursuing PhD from IIT Jodhpur in microelectronics, and my research domain is 2D material based chemi resistive biosensor, and this class schedule is every Tuesday 7 to 9 pm. So we are going to discuss some question answer here, and if you have any doubt then you can ask. So this is the first question. The energy is measured in joules, watt, volt or newton, and I hope all of you know the answer, so please unmute yourself and try to give the answer.
Joules.
Yes, what is the right answer? Okay, Venkata Durga, you can unmute yourself. Najma,
Yes, ma'am.
what is the right answer? The unit of
Joules, ma'am.
okay. So the answer is joules. Okay. So next we are moving towards the next question. So the question number 2 is, identify some of the important process for interdigited circuit fabrication. So first option is the silicon wafer preparation, the second option is the epitaxial growth, the third option is the oxidation, and the fourth option is the all of the above.
All of the
All of the
above.
above, madam.
Okay. Can you a little bit explain about the wafer preparation or the growth or oxidation?
Yes, madam. Yes,
Yes.
madam. Generally, silicon ingot will be taken place and slice it to get the wafer on which we are going for one by one method. Chemical wafer deposition, diffusion, and the final methodology is the metallization to get the MOSFET.
Okay. And Nazma,
Ma'am. Yes, ma'am.
yes, can you little bit explain about these processes, the fabrication process? Because one
Yes,
by
ma'am.
one we will discuss more in more details about the all of the fabrication process.
Okay, ma'am. 98% pure silicon is known as electronic grade silicon, ma'am, which
Okay.
is taken from uh, silicon of 99.9% is pure, ma'am, EGC, electronic grade silicon.
Hmm.
From that, again, by the Chokolsky method, we will extract our required silicon wafer, madam.
Okay. So the right.
That we call
Okay. So the right option is all of the
all of
above.
them.
So next we are moving toward the question number 3. Which one of the following process is preferred from the given dielectric of MOS transistor? So first option is the sputtering, second option is the molecular beam epitaxy, third option is the wet oxidation, and the fourth option is the dry oxidation. Do you have any idea about sputtering, wet oxidation, dry oxidation?
Ambiguity in dry, dry oxidation, madam.
Can you tell me what is the difference between the dry oxidation and the wet oxidation? Why you are using this dry
Yeah.
oxidation process?
Madam, silicon in reaction with H2O, we call that as wet oxidation, madam, forming SiO2.
Okay. So in
Silicon plus water, only oxygen will give you dry oxidation, madam, forming SiO2.
okay, and in wet oxidation,
H2O, ma'am. in reaction with silicon.
And in that case, oxygen is used or only the H2O is used for the wet oxidation process? Can anyone tell? In wet oxidation process, we only use the H2O for the oxidation or H2O with oxygen? Okay, and next question, I think we will discuss more details about this wet oxidation process, dry oxidation process, when we will proceed for the wet oxidation, in which cases we are going to use the wet oxidation process, and what is the difference between this sputtering. Have you any idea about this sputtering system? What is sputtering? In which cases we were using this sputtering? Pradeep, have you heard about this sputtering?
Yes, ma'am. In fabrication, it will come, ma'am.
Okay, so
Sputtering.
Yes, ma'am. Yes, yes.
why
Yes,
we use
madam.
this
Shall I
fabrication
tell the
process?
definition little bit?
Okay, okay, tell.
For forming thin film materials and engraving techniques like that, madam. Sputtering is a physical process which is the vaporization occurs of a solid material by ion energy like that, madam. I remember little bit.
Samuel, have you heard about this sputtering?
Hello,
Yes,
is my voice heard?
yes, your voice is audible. Samuel, please unmute yourself. There is no issue if you don't know about this fabrication process. Today we will deeply discuss about this fabrication process. What is sputtering? What is wet oxidation? Unmute. Okay. Then you can tell me now. Wow, but have you heard about this sputtering? Because here I can see you are not unmute. No, you are not unmute, Samuel. You have to unmute yourself and then tell me. Have you heard about this sputtering? And so one by one we will discuss about it. What is oxidation process? What is the difference between this dry oxidation, wet oxidation, and what is sputtering? Have you heard about the deposition technique and how many types of deposition techniques are there?
Yes, ma'am. Chemical vapor deposition, physical vapor deposition.
And what is the difference between this physical vapor deposition and chemical vapor deposition? Any of you?
Required chemical will be vapors, like in vapor state, it will be deposited on the surface, ma'am.
And how we will take the input, like is in chemical also, in which form you are going to take. Like you are talking about the, like we initially we are talking about the atmospheric pressure chemical vapor deposition. So in that case, how in which form you are taking the chemicals and how you will evaporate?
By heating, madam.
Okay, so you are just giving the temperature some zone, because here you can see what happened in CVD system. Like this is a CVD system. Okay, so this is the gas inlet pipe. Okay, or we are taking the inlet gas like argon. Okay, and there is a quartz tube. Today we mainly discuss about this fabrication process, and this is gas outlet, and it is connected to some of the so here zone 3, zone 2, and this is the zone 1. Okay, up to this. So what we do here, we take in the boat, we take the chemical. Okay, so what happen in that case, we are setting some temperature on this zone, some temperature we are giving here and here, and the temperature is different because each of the molecule or chemicals have different melting temperature. So we used different we set the different temperature in that zone, and then it when the temperature is above the melting point of this chemical, then it start to evaporate. Okay, it start to evaporate, and in that time also we are giving some carrier gas like the argon. Okay, and then it start to flow, and then it start to react, and then it deposited on the wafer. Okay, like that the CVD is working, the chemical vapor deposition. So we are set some temperature, and we are giving the temperature, and it start to evaporate, and there is a carrier gas which we use, and then they are starting to react, and there produces the thin film. Like if we are talking about MOs2, metal oxides, molybdenum sulfide. So what happened in that case, we are taking in zone 2 MOO3 precursor. This is in powder form, and we are setting some temperature is 850, and in zone 1 we are taking the sulfur, and the temperature 200 degree. So we set the parameter like way, when it's reached to 850, then the temperature of the first zone is reached to 200 degree because of the melting temperature. Okay, then it start to evaporate, and we are flowing this argon, and then it is react, and it is form the MOs2, final the MOs2. This is the atmospheric pressure chemical vapor deposition. Okay, and also there are low pressure chemical vapor deposition. This is the deposition technique. And then also the plasma enhanced chemical vapor deposition. Have you heard about this plasma enhanced chemical vapor deposition technique, Pradeep?
Plasma etching, I heard, ma'am.
Plasma enhanced chemical vapor deposition, Pradeep. Actually in that case now, so atmospheric pressure or low pressure, we are setting the temperature very high like 850, 1000 like this. Okay, but when we are going to deposit in the low temperature, so in that case we are using this plasma enhanced chemical vapor deposition. Okay, and oxidation process we will further discuss, and here sputtering is a PVD process. This is the PVD process, physical vapor deposition. And wet oxidation and dry oxidation.
No, ma'am. No.
Hello. Yes, Pradeep. You are not audible. Are you telling something?
Okay.
Okay, so gate dielectric, when we are using the gate dielectric, it is high quality dielectric we are required. So high quality oxide layer will grown by the dry oxidation process, because in the dry oxidation process we are using the temperature, we set the temperature 1200 degree centigrade. Okay, and in that case only oxygen we have used, and then it react with the silicon, and it produces the SiO2. Okay, so this is the dry oxidation process. So why not we are using this wet oxidation and this sputtering? Can anyone tell why not the sputtering or the wet oxidation process? Samuel and Pradeep.
It's a temperature dependent, madam. Temperature
Your voice is not audible. Pradeep, your voice is breaking. Samuel, please unmute yourself, or we can you can write here in the chat box why we are not using the sputtering or wet oxidation process, because sputtering is a PVD process which is physical vapor deposition technique. Wet oxidation is also the oxidation process, but in wet oxidation process what happen, temperature also likely like 900 to 1200 degree centigrade, but what happen in that case, H2O plus O2 then Si, it produces the hydrogen gas and silicon dioxide. You are not able to unmute yourself. You can rejoin, na? Because I have no.
Yeah, yes, madam. I rejoined.
Yes, yes, okay. Samuel, you can also rejoin. I think then this problem, or you can also join from any other. Okay. So what happened for the sputtering and what happened for the wet oxidation process? See, when we are using this wet oxidation process, now we are using this H2O and also the O2 and silicon. Then it produces the hydrogen and also the oxide. What happened in this case? This is uh, uh, like in small duration or a small time, the growth is very fast in wet oxidation because of the H2O vapor. Yes, because of the H2O vapor the growth is very fast, but the quality is degrades because of this H2. Okay, that's why we are not using the wet oxidation process, but in dry oxidation process it's a the process is very slow. It's require very, so much time comparison to this wet oxidation, because here only we are using this O2 and also it reacts with silicon and then it produces the silicon dioxide. But the quality here you can see no other only the silicon dioxide is produces, no other the hydrogen or something else. Okay, so the quality is very good. That's why we are using here because in MOS structure there is a metal, then oxide, then semiconductor. So we required very good quality of the oxide layer. That's why we are using this dry oxidation, not the wet oxidation, because here we are using the H2O. That's why the hydrogen is produced and this hydrogen degrades the quality of the oxide layer. And sputtering also the quality. Mainly here we are using the dry oxidation process because of the quality. Okay. Do you have any other doubt? Then move towards the next question, question number 4. So identify the type of package that has been used in dual inline package and single inline package. The first option is the through the hole package, the surface mount package, and the through the block package, and fourth option is the none of the above. So what is the right answer?
Whole package, madam. Whole package, madam.
Okay. So the right answer is through the whole package. Next we are moving towards the question number 5. So which of the following is not a factor in CMOS total power consumption? The first option is the average switching frequency, the second option is the supply voltage, the third option is the transistor resistance, and the fourth option is the load capacitance.
Resistance, madam. Transistor resistance, madam.
Samuel, what is the right answer?
Okay, madam. In phone, I mean.
So what is the right answer?
I'll tell, madam.
Okay, take your time, but at least try. Today we are mainly discussing about the IC fabrication process, how you can further, if you have any interest in further study, so you can go also from in the field of fabrication. That's why I am little bit.
Transistor resistance, madam.
Yes.
Transistor resistance.
Can you explain how the transistor resistance?
Uh, so total power consumption is from charging and discharging by capacitors and supply rail supply rails, switching from supply rails
Okay.
and leakage.
Okay. Pradeep,
From
can you?
that total power consumption
Yes,
will be there.
yes, madam. I will explain, madam.
Yes.
The total power consumption is due to the static power consumption, dynamic power consumption, and short circuit power consumption. In static, VDD multiplied by ID, so supply voltage comes there. When you go for dynamic, CL VDD and CL VDD square alpha into F. In that also frequency covers and load capacitance covers, whereas switching frequency also covers there. Even for short circuit also there is no resistance component. That's why the not a factor of CMOS total power consumption is total resistance, man, transistor
Okay.
resistance.
So can we write the power dissipation like this, CL into F into VDD square?
Alpha, there is a switching factor alpha also we should write.
Okay. So here CL is the load capacitance, and F is the which frequency?
Which is correct, madam?
Sorry, what? But is the right answer here? Switching frequency and VDD, the power supply voltage. So here also you can see that the power is a as you have told earlier. Just so this power is the factor of CL, F and the VDD also, and it is not the transistor resistance. So can we move towards the next question, or do you have any other doubt?
Okay, next, madam.
Okay. So the question number 6 is the statement 1. The most significant parameter in CMOS power consumption is the supply voltage VDD, and the statement 2 is increasing the power supply voltage VDD will decrease the speed of performance of CMOS gate. Which of the following is true? The first option is only statement 2 is true. The second option is both the statement are true. The third option is both the statement are false, and the fourth option is only the statement 1 is true. So please go through the question carefully, and I think all of you can give the answer. Am I audible? Hello? Hello, am I audible?
Audible,
Yes, madam.
We are thinking.
Audible.
Okay. Please take your time, but at least try.
Option D, madam. Only VDD is one of the parameter. Second one is wrong statement, madam. That's why option D is the correct answer from my point of view.
Okay. Samuel, what is the right answer?
Thinking, madam, just.
Okay. Take your time.
D, madam. D only.
Okay. Can anyone explain? Samuel, can you explain?
Okay, madam.
Why only option D?
So power related to, as per that formula, madam, power dissipation, dynamic power,
Hmm.
total power is called total power dissipation. In that dynamic power is mostly considered, so that there in that VDD square will be there
Okay.
in power dissipation, and due to that power,
Uh, Pradeep, can you explain? Yes,
Yeah,
the answer
same
is
thing,
right.
madam. Uh,
Okay. So we are moving towards the next question. So here the question is the statement electrical effort H is the
madam,
ratio.
madam, just give previous question, madam. Just 1 minute. Just I will take for nap.
Okay.
Okay, thank you, madam.
Samuel, you can go through the PPT. Na, I have uploaded it on the link. I think you got the link, na?
Okay, madam. Okay,
So from
okay,
there you can see all the question. Okay.
okay. Thank you.
So this is the question number 7 statement. The electrical effort H is the ratio of the output capacitance to the input capacitance, which is defined by the H. So is the given statement is true or false?
True, madam. True, madam. Capital H is for the path, single is for electrical effort. Correct, madam. Correct.
Okay. So the right option is should be true. So this is the question number 8. Consider a CMOS inverter with C equal to 10 F farad. So VDD is 1 volt and the propagation delay TP is equal to 10 picosecond. So find the energy delay product when the inverter is operated in its theoretical maximum possible operating frequency. So this the first option is 50 into 10 to the power minus 27 joule second. The second option is the 40 into 10 to the power minus 27 joule second. Option C is the 70 into 10 to the power minus 7 joule second, and the fourth option is none of the above. So at least try. Energy delay product you have to find. There is no hurry, you take your time, but at least try, all of you. Yes. So what is the right answer, Shurajit? I think there is a small mistake in this equation. You have written the CVDD square into TP0. So please correct it. There is a small mistake. Yes. So calculate it. Okay. Pradeep, what is the right
I am
answer?
calculating. I am just calculating.
Okay, okay, take your time. Samuel, there is one more student. Samuel.
Formula I don't remember, madam. For actually for mm,
you take your time, but
for energy power into time, no, madam. So for power, V is there, I is not there. So V into I into T, power into delay time is the energy.
at first try, then I will say. ये 2211265. What is the right answer? I'm not able to see your name. After 10 question we are going to discuss about the fabrication process, each one of the fabrication process. So we will start from the wafer cleaning, then oxidation, then deposition techniques, then lithography. Pradeep, have you calculated?
Getting option A, madam, 50 into 10 power minus joules.
Okay. Samuel, have you calculated? See, energy delay product equal to, what is the formula, Pradeep?
Madam, just I am taking power by time, and 1 by time is I am taking frequency. I am doing like that.
Okay. So you can calculate also like this way: half CVDD square into time delay.
Yes, ma'am.
Okay. So just put the value. What is the value of C here? C is 10 F to 10 to the power minus 15. And what is the value of V? I think 1. And then what is the value of TP? TP is 10 picosecond. Pico 10 to the power minus 20 second. So total is joule second. So total value is 50 into 10 to the power minus 27 joule second. Someone have you got the answer? How we have calculated? This is the answer. Just we are multiplying this with this power. Okay. Someone?
Yes, madam.
Okay. So can we move towards the next question?
Yes, madam. Yes, understood.
So this is the question number 9. Calculate the small signal voltage gain. Calculate the small signal voltage gain of the circuit shown in the figure. Shown in the following figure.
GM1 into R01 parallel R02, madam. GM1, madam. For a telescopic connection, the transconductance is transconductance of the first transistor and multiplied by parallel resistance of RDS2 parallel RDS1. So option is B, madam.
Okay.
But there will be one minus sign.
Gain, sir, we are taking magnitude, sir. Yes, sir.
Oh, do you have any doubt in the previous question?
Yes, yes, the sign only minus because conscious contribution is there.
Okay, okay. Here we are just taking the magnitude. This is the
Oh,
question number 10. Samuel, have you understand the previous question?
Yes, madam.
Okay. Durga Prasad, I think. Durga Prasad, please unmute yourself and try to give the answer. Have you understand the previous question? Durga Prasad?
Not that much, madam. State trial.
So this is the question 10. Find out the value of, yes, there's so much noise is coming. So find out the value of logical effort of the given circuit whose delay is equivalent to the CMOS inverter, whose WP by WN is R by 1, where the WP and WR are the width of PMOS and NMOS respectively. So what is the right answer here?
Madam, generally for the NOR gate, 2n plus 1 by 3, madam. But here I am not finding that answer for 3 input means 2 into 3 plus 1 by 3. 1 minute, madam. Give me time. I am checking.
If you are not able to do this question answered, then it will your homework. Next day you will explain how to solve it, because in the lecture videos are also taught how to solve this type of problem. This will be your homework.
this will be a NOR gate, no? Why it is AND gate?
Just tell me how you will calculate the logical effort and which one is the right answer.
Ma'am, option C, 3R plus 1 by R plus 1.
How you have calculated? Can you explain?
Yeah, with respect to inverter, I am checking and I am doing that one. Man. Inverter is sizing 2 by 1, PMOS with 2 by 1. Then we are applying that principle for the NAND gate and NOR gate. Like that I am doing, madam.
Yes, the right answer is option C. 3R by 3R plus 1 by R plus 1. Can you again explain
Yes, madam.
how you have
Generally, when we are
at
going
first
for
there are three R. Okay, so at first what you have done?
3R, madam. Yeah, PMOS 3R and NMOS is 1. 3R plus 1
Okay.
by R plus 1 is with respect to the inverter.
So now we are starting to discuss about some of the fabrication process. So have you heard about this photolithography process?
Yes, yes.
Can you little bit explain what is photolithography process and what we did in this
To
process?
get the selection portions of a substrate on which we are going to diffuse n plus source and diffuser. So for that reason, photolithography process is there. Selective area within that etching process will taken place and all that.
See,
Yeah, some more
photolithography is
maybe.
a total process, like it is a pattern transferring process. Surajit Ravidas, have you heard about this photolithography process and what do we understand by this process, like what we do? Can you little bit explain?
I'm actually unaware of this topic.
Sorry,
Richard.
you are not audible. Hello. Samuel, can you explain about little bit what is the photolithography process? Have you heard about this photolithography process? What we do mainly? can you can mute yourself actually there noise is coming. There is a light source, okay? And this is a mask. Like if your ID pattern, if you want to, this is the ID. So like this is the opaque portion. See, please see carefully. This is the opaque portion, so light can't pass through it, and this is the transparent area, and this is the mask, optical mask. The light is coming from this side, and here is our wafer. Okay, and there is a photoresist covered it. Photoresist, and what happened in that case, there is a light source means UV light. From some second, like 8 second, 10 second, we exposed it, this light on this mask, and what happened, this pattern, there is a pattern na, this is opaque and this is transparent. So light is passing through it and it is falling on the photoresist. Can anyone tell what is photoresist? Pradeep, what is photoresist?
Yes, madam. There is a opaque area on which only certain portions of these things allowed light, remaining portions not allowed based on the materials.
Okay. So photoresist is a photosensitive material. Okay. So when this
Yes.
light coming from this, like this is the opaque portion and this is the transparent. So what happened in that case? When you dip this the structure on some solution, some etching, okay, in development solution, there is a development solution. You dip this into this. What happened in that case? Because there is a two type of photoresist. One of them is positive photoresist, one of them is negative photoresist. So depends upon the type of the photoresist, it will act. So it will remaining some of the portion, like this ID pattern will stay. If it is a positive photoresist, this ID pattern will stay in the photoresist, or remaining portion will dissolve into this development solution. Okay. So you will get this type of structure after the development, like this ID pattern, like is only this pattern. Okay. And the remaining portion etch out, and there is a oxide layer is present. Okay, this is the oxide layer. This is the photoresist. And what happened after that? After that you will dissolve into some of the solution for the etching. So you can, for oxide layer you can etch out by the dipping the HF solution. So if you etch out, this portion will cover na, so it will act as a mask, like it will cover that portion, and the uncovered portion will etch out. So you will finally get on this oxide layer or something, or if you are like, if you are deposited previously in gold, so you can get that type of shape, that type of pattern on this wafer. Okay. So this photolithography technique is a pattern transferring process. Now it is clear, there is a pattern which is in the mask, the optical mask, which is transferred onto the wafer. Okay. This process is called, this whole process is called photolithography. Have anyone any doubt? Pradeep, it is clear up to this?
Yeah, ma'am.
So this is the pattern transferring process. From the mask it is transferring by this process, it is transferring into this wafer. Okay. So this is the pattern transferring process. So can we move towards the next question, or do you have any difficulties or any understanding difficulties in the photolithography process? Because when you are going to deposit fabricate some devices or the IC, this is the very important process. This is the photolithography, and the whole things like etching, development, soft bake, hard bake, this process is including on it. And mainly in online we can say that this is the pattern transferring process on the silicon wafer surface. Like if you want to deposit or pattern some of the gold electrode, so in that case you can deposit the at first you can deposit the gold, and by this using this mask you can then pattern. Okay. So from the mask to that wafer surface you are transferring the pattern, it is called the photolithography. Nazma, have you understand what is the photolithography process?
Yes, ma'am.
Okay. So can we move towards the next question?
Yes, ma'am. Yes, ma'am.
Okay. So question number 12 is, what is a oxidation in fabrication process VLSI? We have already discussed about the oxidation process, right? So can you right now explain it? What is the oxidation process and type of oxidation process?
Two type of
Pradeep, what is the oxidation process?
madam.
Yes.
It's formation of SiO2.
Pradeep, what is the oxidation process?
Yes, madam. There is a formation of layer with some chemical reaction. Either we O2 or H2 or like that. There is a formation of layer, madam. It does not involve oxygen or like that.
Like if you want to grow the oxide layer,
Yes, madam. Yes, madam.
so this is to produce, like the oxygen is reacting with this silicon and it produces the SiO2, right? This is the oxidation process. So what is the process here? It is also included in the dry oxidation process and wet oxidation process. And what is the difference between these two? Only Si plus O2 which produces the SiO2. And what is the wet oxidation process?
Two, madam. Yes, sir.
You can see the equation. Okay, so mainly the water vapor, oxygen, and then silicon reacts and it produces the oxide and the hydrogen. So this is a question, what is photoresist and type of photoresist? You have I have already shown in the photolithography process, when pattern is transferring from the mask to the wafer surface. In that case, at first we have to do the UV expose, like there is a UV light which is exposed on the mask, and in between in the below of the mask there is a wafer. And what happened in that case? we need, there's a light source, the light is coming, this is the mask, there is some pattern is there, optical mask, and from the mask the light is coming when the wafer surface, and here is something if there is a deposited material or there is a photoresist. Okay, this is oxide, at first take this is oxide or some gold layer, and then there is a photoresist. So now tell me, what is the function of photoresist here? Why photoresist we have used? What is it?
For patterning, madam, we have positive photoresist and negative photoresist.
So what is the work of photoresist? Like if we are not deposited the photoresist or spin coat the photoresist, what happen in that case? Can we directly use the optical mask on the wafer or some deposited, like we want to see, this is the wafer, then there is we want a gold electrode over it. Okay, the gold electrode, like that, in that portion we want the gold electrode. So if we are not on it, we are spin coated the photoresist, what happen? In that case what happen? If we do the lithography process, there is a light source and it is coming from this mask and directly on the gold, this is totally gold, because we want the gold electrode, and here is the gold electrode pattern is there. So what happen if we are not using the photoresist? Do you have any idea? If we are not using the photoresist, in that case what happen? Nazma, this is the main work of photoresist.
To protect the region that is not to be removed, ma'am.
Okay, it is little bit true, but at first when we are exposing in the light, now in that case what happen? There is a photosensitive layer. Photoresist is a photosensitive layer. Like if it is a bright field mask, what happen? This is the opaque portion, na? Only this opaque portion will remain. Okay, you are giving the UV expose, and which is transparent in this mask. So here when you dip into the developer solution, na, after the UV expose, when you dip into the developer solution, this is the developer solution, what happen? This is opaque portion. If it is a bright field mask, then this portion photoresist, this is covered with this opaque portion, na? So it will stay this because it is a light sensitive, and the other portion where it is the mask is transparent, that will gone. So then what type of structure you will got? This is the AU, means gold electrode we need, na? Then only the remaining portion of the photoresist there. Okay, that portion. So what happen? It will protect the underlying layer. So when we dip into the etching solution, what happen? Only that portion will stay. After that, only that portion. Oh, sorry, this is not. Only that portion. This is gold and this is photoresist. Now it is clear what is the work of the photoresist. This is photoresist. Sorry, this is AU gold and this is photoresist. Pradeep, is it clear? This is the photosensitive layer.
Yes, ma'am. Yes, ma'am.
Okay, when you are going for the UV exposure, then it is coming from this mask, so this is sensitive. That's why only this portion will remain when you will dip into this wafer into the developing solution. Okay, so in developing solution, which is the portion of transparent na, that portion will gone, but which is the opaque portion, it will stay. Then what happen, this type of shape we will get. So it will protect as a mask, so it will protect the remaining area. So after that, when we go for the etching, then the underlying layer will stay and the remaining portion will gone, like that. Then you can use the photoresist removal solution, and you will got the final structure, the gold electrode. Okay. And the type of photoresist, sorry, type of photoresist,
Negative and positive.
and what is the difference between the negative and positive photoresist?
And some portion, whenever exposed portion to the light in positive photoresist, that will be etched, whereas negative portion, whereas exposed areas will be pattern, next pattern.
See, if it is there is a silicon wafer and there is a photoresist, positive photoresist, okay, like that, this is silicon, this is positive photoresist, and this, there is a UV exposure, and this is a mask. What happen in that case? It will protect, if it is a positive photoresist, it will protect that portion, or it will protect that portion, or it will protect this portion. This is one region, this is two region. Which one will be
Protected in negative, madam, whereas in not protected in positive.
like which is covered with the positive photoresist, it will stay in the developing solution, and which is not covered, this portion will etch out. Okay. And in negative photoresist, what happens? The opposite is happens, because the covered portion will be like the will etch out, and the uncovered portion will be harder. Okay.
Yes, ma'am. Yes, ma'am.
Okay. Then what is a mask in VLSI and its type? We have already discussed about the mask. From the mask, the pattern is transferring in from the pattern is transferring on the wafer surface. Okay. So now tell me, what is the mask? What is the work of it? And the type of mask. This is a mask. So in the mask, we can see different type of shapes like that. So you can see the red color portion is the opaque portion. From there the light can't pass, and the remaining portion is white. So this is the transparent, and this in here only that portion, like there is a structure you can see, and the remaining portion is black. Only the portion we want to pattern, and the remaining portion is black. Now you can see the difference now. The remaining portion is black here, only the where you want to pass, this is smaller, and here the opaque portion is the red color, and this is the transparent. So which one is positive, and which one is the bright field mask, and which one is the dark field mask? So there is a two type of mask is present. One of them is bright field mask, and one of them is dark field mask. Can you see the difference? Here the maximum area is covered, or the opaque portion. Only the portion you want to transfer the shape, the pattern. This is only the white color portion, and maximum is covered. So you can see there. You can if you can see, then you can see the only the dark. The remaining, the maximum portion is dark. That's why it is called dark field mask. And here you can see the maximum portion is white. It means the transparent. Only the opaque portion is the pattern you want there. So this is called bright field mask. Is it clear? Is it clear or I have to explain again? Nazma?
Yes, ma'am.
Now the next question is, what is meant by etching process and type of etching process? You have heard about the etching process and IC design
Yes,
and
ma'am.
also the device fabrication. Etching is the most known process. So what is the main what do you mean by this etching process? What do you do in this process?
Removing the required portion we call as etching, ma'am.
Okay, and the type of etching process?
Chemical etching, plasma etching,
Okay, so
X-ray beam etching.
have you Pradeep?
Yeah, yes, madam. Dry etching and these things. Actually, we are removing unwanted portions, madam. That's only remember by using some chemical process.
Okay, so there is a mainly two type of process. Okay, one is the dry and wet etching process. Can you give the example of the dry etching process and the wet etching process? Nazma? Dry means from the dry word what you can
X-ray, like X-ray beams, plasma, maybe under dry etching, ma'am. If we use chemicals, that will be wet etching, ma'am. Like
chemicals means if
hydrofluoric
there is a
acid
solution is present, like in solution some chemicals are present, in that case you can
solution.
tell it is a wet etching, like PIMA. You can go through some of the process with PIMA, tetramethyl ammonium hydroxide. So and the reactive ion etching, deep reactive ion etching, some ions they are bombarding, so the remaining portion can etch out, the required portion can etch out the ion. So this is the part of the dry etching. And wet etching, there is a solution. So if you dip the wafer into the solution which is not covered by the mask, it will etch out. Okay, so can you move towards the next question?
Yes, yes, ma'am.
Yes, ma'am.
So have you heard about the word the doping? What is
Yes, ma'am.
doping
Yes,
and
madam.
the method?
Adding impurities to the pure silicon, it's a contamination that is called doping. Doping is to improve the conductivity, ma'am.
Or main methods? What are the main methods? How you will introduce the impurity?
Um,
By the method of epitaxial layer, madam. Epitaxial growth.
No, actually there is two well-known processes are there. Have you heard about the diffusion process?
yeah, yeah. Diffusion and
If there is a
implantation.
Yes,
MOSFET,
ma'am.
you can see here there is a oxide layer and this is a metal layer. How you will like N plus E, grow the N plus region. Okay, so in that case we have to diffuse or the ion implantation. Diffusion and ion implantation. Have you heard about the ion implantation? And what is the meaning of the diffusion? What happened in the diffusion process? Any idea?
We will fill the required region with the impurity atoms, madam.
See,
Impurity gases.
diffusion means the movement of the movement from the higher concentration to the lower concentration. If you are adding some impurity and it is moving towards the higher to lower, in that case you can tell it is a diffusion is happening. And ion implantation is bombarding of the ion or diffuses the ion. Diffusion is this is adding impurities by the ion. Okay, bombarded the ion. So in that case, the ion is goes to in that portion, and it can added the N plus region, make the N plus region. So is it clear?
Yes, ma'am.
Samal?
Yeah, yes, madam. Concentration gradient diffusion, drift like that ion implant.
Oh.
Ma'am, ma'am.
Yes.
Then what is epitaxial growth, ma'am?
Pradeep, have you any idea what is the epitaxial growth?
I have to recall, madam. I am not in a position to tell you.
Samuel, have you heard
One,
about the epitaxial growth?
yeah, layer by layer growing like oxidation is epitaxial process, madam.
Or anything else? So dry oxidation we can tell like there is a one layer is present, then we are growing another layer. Okay, then we are growing some different layer. So can we tell it is a epitaxial growth?
Yes, ma'am. Yes, ma'am. Yes, ma'am.
So is it clear, Nazma?
Yes, ma'am.
So layer by layer we are depositing something, so it can tell the epitaxial growth. So what is the deposition in fabrication and type of it? So we are discussing about the deposition technique. I think in the starting of this session we have started with the deposition technique. Some processes are there, some chemical process, some physical techniques are there to deposit some material on the wafer surface.
Yes, madam. Actually, for forming of source and drain, we are going for diffusion and ion implantation. For forming of gate, we are going for chemical wafer deposition technique.
Forming the gate, okay, on the oxide layer. So what happened in that case? Deposition technique statement, we are depositing, there is a wafer surface, okay, so we are depositing some material on the wafer surface. So if you want to grow the oxide layer, this is also the portion of the depositing. Now we are growing the oxide, and also if you want to deposit the metal or something else, in that case also it is deposited. So there are some techniques are present like the CVD techniques. We already discussed it, and the CVD technique. What is the full form of CVD?
Chemical
Chemical
wafer
vapor
deposition.
deposition.
And the physical vapor. So in chemical vapor technique, there are too many techniques also are present, including it. Like, can you tell anyone in CVD process which process are present? Like the different type of CVD process. Can anyone tell? Have you heard about the atmospheric pressure, chemical vapor deposition? I already discussed it. And the low pressure chemical vapor deposition, and the plasma enhanced chemical vapor deposition. And any of the material we deposit by this chemical vapor deposition, can anyone tell? Tell me. Any material you can deposit by the CVD technique.
Uh, Alumini pattern, madam. Alumini pattern.
Aluminum
Polysilicon pattern, polysilicon.
Polysilicon. Anything else?
Mm.
Take your time and try at least try. Oxide layer. Can we deposit by the CVD process?
No, ma'am.
Madam, carbon nanotubes, graphene and polysilicon. Madam.
Okay. And by CVD process?
Pattern polysilicon gate alignment.
Okay. Polysilicon gate. So can we deposit some metal from previous
Yeah,
CVD
yeah,
technique?
yes, madam. Yes, madam. It is possible. Metallization.
And in the PVD technique, there are three types of techniques are present. Can anyone explain?
One technique you already explained, sputtering, madam.
Sputtering. Another? One day we will explain about more details about the sputtering, thermal and e-beam. The next process is the thermal. So in sputtering and thermal, and third one is the e-beam. So can from the definition or from the like thermal e-beam, can anyone little bit explain what is it, how it will help to the deposition, how you would deposit? Anything, any idea? Little bit. This three
The
sputtering, thermal evaporation and e-beam. These are the PVD technique, physical vapor deposition. We can mainly deposit the oxide layer like SiC in 4. By sputtering we can deposit, okay, like aluminium, chrome, gold. By well known the thermal we are depositing. E-beam also gold. Okay, these are the examples. So little bit we can discuss about this sputtering, thermal or e-beam process. Do you have any idea? Take your time and then at least try. Then we will move towards some numericals, small numericals for MCQ question. Actually, these are the overview of the fabrication process. Like in deposition process, what we do, in oxidation process. Because when we are going to fabricate any chip, this process you have to know how to fabricate this chip or a device. So some techniques are required to fabricate this device. The main important thing is the photolithography process and the deposition process, and the photolithography, the deposition, the etching process, and these are the techniques like the CVD process, the physical vapor deposition process, and there are so many processes in this, including this PVD like sputtering, thermal, e-beam. So what is the main difference between what is the main principle of this sputtering, thermal or e-beam? Take your time, but at least try. Then we will move towards some numerical questions.
Ma'am, I have an idea. Is it correct, ma'am? In E-beam evaporation process, a high energy electron beam is used to heat the. Ma'am, I have an idea. Is it correct, ma'am?
Can you
In
please
E-beam
unmute yourself?
evaporation process, a high electron beam is used to
Someone please mute yourself. Yes, Nazma. Yes, you are right. A high electron beam. Okay, then after that, what happened?
is used to evaporate the chemical that we want to deposit as a layer, madam.
Yes, like if there is a sample holder and here metal layer, mostly we are depositing here the metal. Okay, so the E beam we are putting here the high electron beam, and then this portion will deposited heat it, and it deposited on the wafer surface. Okay, here this is deposition is taking place. Yes, you are right. And what happened in the thermal?
Temperature is used to heat.
Yes, like temperature there is a board. Okay, and there is a like gold. Here the gold is present, and we are high current is passing through it, so it heated up the and it is its melting point is greater than the melting point of gold. If you want to deposit the gold, here the gold is present on the board, so high current is flowing through it and it is heated up, and then gold starts to evaporate and it is deposited. Here is a sample, so sample means the wafer, so on the wafer the gold is deposited. Here the gold is deposited. Okay, yes, you are right. And sputtering? What happened in the sputtering? Pradeep, Kamal?
Forgotten, ma'am. I have to refer.
Okay, like here is your there is your wafer, and there is your target. Like this target is silicon nitride, Si3N4. Okay, we want to and this is my silicon wafer, so we want to deposit here we want to deposit the silicon nitride. What we will do, and this is a closed environmental loop. Okay, just in the sputtering system, so we will flow the target gas like argon. It will, and there plasma is generated there, and what happens, the argon ion is bombarded on this target, and it will, when it is bombarded, so some portion of the target is going through that silicon, and here it will deposit. Okay, so now you can see the difference. First, in E beam, the E beam is very high electron beam is using to evaporate the metal or material. In thermal, we are mainly using the temperature, like we are flowing the high current, and it is then the material will start to evaporate. Okay, and in sputtering, there is a target is present, and also the target ion, the argon ion is bombarded, and also it start to deposit, and some of the portion of the target is start to deposit on the silicon. Now it is clear up to this?
Yes, ma'am.
Pradeep?
Yes, ma'am. Yes, ma'am.
Samar? Do you have any other doubt?
Ma'am,
Yes.
for fabrication, which textbook is a good one, madam?
Fabrication textbook.
Yes, ma'am. Which one is the preferred book, ma'am?
Just a minute. not able to remember the book name. Just a minute. No.
SMG, madam. VLSI technology by SMG.
Yeah, one more another book we have used for the
Gandhi.
fabrication equipment. कौन सा book पढ़ते थे?
Microchip.
C से ना
NK
सारा
Gandhi
book एक और
something.
book है. It's one more book is there, well-known book. Just a minute. One more another book.
JD
Plumber. Yes, Plumber. JV Plumber. Okay. PLU Plumber. Okay.
JD Plumber. J.D.
D. Okay, you can follow this book.
Stephen also one.
JD Plumber. Actually, I also read this book, JD Plumber. I forgot the name. Nazma,
Yes, ma'am.
you can follow this book.
JD Plumber.
Or next day I will share the link. If I have, I will find out. Then I will share. Okay.
Okay, madam. Please share it, ma'am.
Okay. I will. Share.
Thank you, ma'am.
Okay. So now we are going to solve some of the numericals. There are MCQ types of numericals. So tell me the right answer. The measured transconductance GM of an NMOS transistor operating in a linear region is plotted against the gate voltage VG at constant drain voltage VD. Which of the following figure presents the expected dependence of the GM1 VG? So what is the right answer, Pradeep? The measured transconductance GM versus VG.
Give me a minute, madam. Give me a minute.
Okay. No worries. If I find the link, na Nazma, I will share it on the where I am sharing the PPT. Okay, there I will share.
Okay, ma'am. Ma'am, I have a doubt where the PPT will be available, ma'am.
Actually, they have already shared the link. From there you can access my all the PPT.
Okay, ma'am.
If you want, then I can also share in the chat.
Yes, ma'am. Please.
Just but it will take some time. So at least
Okay.
you try this, and then I will share.
Is the answer is D, ma'am?
No, not
Option A, madam. After variation, it will falling down.
yes.
Option A, madam. Option A.
How it is?
Yeah, you are saying in linear region, na, madam. Linear region means transistor will act as a resistor after some portion of Vg, again transistor move on to the saturation region. Then
Can we write like mu and COX W by L like beta? Can we write it?
yes, in linear region we can write it down. Vgs minus Vt into Vds minus Vds square by 2.
So what is the value of transconductance here?
Uh, Vgs minus Vt, Vgs minus Vt,
Okay,
Vds
and
divided by 2.
VDS constant.
Yes, yes, yes.
Then tell me from here, tell me what is the value of GM.
Then option is not matching, madam. Inline which should be become, should come in line with the,
At first tell me the value of GM when VDS is constant.
yes, yes.
Just derivative this ID with the
Then
same.
beta only will come. Beta only will come, madam. Beta only will come.
So
Then mu
beta will
and
come and
Cx,
then
nothing, nothing other than that, nothing will come. Then options are not matching.
Beta into VGS minus VT.
VGS minus VT into this VDS is constant, so it can write into VDS. Actually, when x minus 1 in the derivative portion, can you remember this? What in the respect to x, what you write in that case? Like if you are taking some square, so in that case, the whole portion you are imagining like x. So that's why 2 into x minus 1, okay, then 2 minus 1 into the dx of this x minus 1, like that.
Correct.
Okay, so in here also you are writing like this. Okay, so beta into VGS minus VTS into VDS. So now tell me, this VDS is constant, the beta is constant. Now what is the relation between this GM and VGS?
Directly proportional, ma'am.
Yes, GM is directly proportional to the VGS. So which
Option
Option
C.
C.
solution?
Option C, madam. Option C.
Okay. Someone, is it clear to you? Can you move towards the next question?
Yes, ma'am.
Madam, is it applicable for saturation region also?
In saturation region, you just tell me, in saturation region what happened? It will independent of the VDS, or what is the value of GM in that case?
Yeah, then that is also mu and Cx into Vgs minus Vt. Even Gm directly proportional to the Vgs, na?
If the see, if GM
Hmm.
is directly proportional to the VGS, in that case also it will follow the same.
Okay, fine. But okay, correct, ma'am, correct.
Only you just have to see the equation, okay, the ID equation, and then you have just to find out the GM. If GM
Oh,
is directly proportional, then it will follow this. If it is not, then it will inverse or something else.
but when you go for technology bias, Gm is equal to 2ID by Vgs minus Vt. Then how to think about Gm and Vgs variation, madam?
Like you were telling about GM is equal to, tell me the equation.
2ID by Vgs minus Vt.
2 ID.
2ID by Vgs minus Vt. 2ID by, madam. 2ID by.
ID here is present.
Yeah, actually, madam, when you go for in saturation region, ID equal to mu and Cx Vgs minus Vt whole square by 2 into W by L. If you differentiate, you are getting mu and Cx W by L Vgs minus Vt dou ID by dou Vgs, and then if you substitute from the current equation, we will get three equations. One you are placing mu and Cx W by L, and another one is Vgs minus Vt. Then I am getting three types of equations GM. So based on your sentence, I understand that we need to see the other parameters constant, and GM
No,
is
no,
how
you
it
have
is
to,
varying.
here you have to see now the ID is constant or not.
Correct, correct,
Okay,
correct.
here if any function of this ID is depending on it. So in that case you can't tell that it is directly proportional. Here is the beta is constant, the VDS is constant, that's why this VGS is directly proportional.
Correct,
Like
ma'am.
at first you
Correct.
have to find out this ID is constant or it is having some variable, it means the variation parameter. Okay,
Yes, madam. Understand.
then you can find out the relation between it.
Yes, ma'am. Yes, ma'am. I'll follow.
Okay. So this is the question number 19. If the drain current of a MOSFET in saturation is given by ID equal to K into VGS minus VT whole square, where K is a constant, the magnitude of the transconductance is GM is. Just directly you have to require this formula. Then you can find out the value, the magnitude value of the GM. Just you have to find out the magnitude value of. Tell me which one is the right answer.
Is it B option, ma'am?
Yes, the right option is B. Tell me how you have find out. Just here you have to write this del VGS. Instead of ID you have to write the K into VGS minus VT whole square. So what is the right answer? K is constant, it is coming out 2x square. I have already told how to derive 2 into x to the power n minus 1, like 1 here, okay, and dd x of this whole things, so it will get 1. Okay, so this is the right answer. Here is 1, so right answer is 2. Pradeep, is it clear?
Yes, madam. Understand. Simply do ID by do VGS.
Just
Correct.
simple derivation. So and then question number 20. In the circuit shown below, for MOS transistor, nuance Ux is 100 and the threshold voltage is given 1 volt. The voltage Vx you have to find out. Now tell me what is the value of Vx. Nazma, you can wait after the session. You can wait for 2-3 minutes. Then I will share the PPT link. Okay, in the chat box.
Okay, ma'am.
Please try to solve. I'm coming back in 1 minute. Please try to solve it. the right answer?
Madam, there is no ID now. Only we are writing ID equation upper transistor and lower transistor.
Yes.
We are equating. That's correct now. Vx
Yes,
into
yes, yes. Just see in which mode it is operating, like saturation or linear region, and then just ID1 and ID2 is equal because the same current is passing through it. Okay.
correct, madam.
Yes.
3.67 I am getting, madam.
Okay. Anyone else? So at first tell me in which region it is operating. It is linear or saturation,
Lower transistor in saturation region,
and the upper.
upper transistor VDS.
You can take
Yes,
like
madam.
VD upper greater than is VG minus VTH. It is 6. We can see 5 minus 1. So is it satisfying? So what is the condition where upper also in saturation, and the lower one is also saturation, because here also the VD is greater than is VGS minus VTH, because here these two are short and this is 0 ground. So VD is always greater than, and here the VT is 1. So whatever the value is here now, so VD is greater than VGS minus VTH, because if the VDS is Vx in the lower, then it will greater than the Vx minus 1. So whatever the value of VGS, it will greater than the VDS. So in the both it is saturation. Is it right or anything else? Pradeep?
Both are in saturation region.
Yes. Then what is the equation? ID upper Nazma equal to ID lower.
Yes,
Tell me
ma'am.
the equation.
Mu and COX W by L into VGS
VNCX
minus
W by
VT.
L into 5 minus Vx minus 1 whole square by 2.
Okay, just a minute. Okay, so we can cancel out this mu and COX from the both side now.
Correct, ma'am. Correct, ma'am.
So there is a W by L upper side, okay, into
4 times, 4 times.
yes, this is 4 times. We'll write later. Then what is the value of this
5 minus Vx minus 1 whole square
VGS 5 minus 1? I think there
minus
were
Vx.
see here the Vx is present. So VGS
Correct.
is 5 minus Vx minus 1.
Vx minus 1.
Yes,
Vt 1.
Vx minus 1. VGS minus VTH whole square, right?
Correct, madam.
And
Whole
in
square.
this side, W by L is 1, lower side, and the equation is
Simply Vx minus 1 whole square.
yes. Then this side we will get the 4 into 4 minus Vx whole square, and
Whole
in the
square.
side Vx minus 1 whole square. Can you cancel out from both sides this square like that? 2 into 4 minus Vx, right? Vx minus 1. Can we write it?
Not possible, na, madam. It is 4 minus Vx square. This is V. Okay, root out. Correct, ma'am. Correct.
Root. This is 3.
Root out.
Root out. Okay. So we can
Yes,
write
yes.
8 minus twice of
3
Vx,
volts, I think.
Vx minus 1. So we can write Vx equal to 3. Right? Can
2
we
volts, madam. Vx is 2 volts. Vx is 2 volts.
uh, you are not able to see
3,
my
3, madam. Okay.
just a minute. Am I doing any mistake, or can you recheck again?
But
I think we have done some mistake here, or VGS minus VT. voltage, and 4 minus 4 minus Vx into 4. Okay, we are just have to, okay, 2 4 Vx minus, so this side minus 1 and this side plus 1. So just see here, minus 3 Vx and this side plus 8 plus 1 is equal to 0. So minus 3 Vx, this side if we are taking from 9, so Vx equal to 3. Is it right,
Correct, ma'am. Correct.
Nazma?
Yes, ma'am. Ma'am, I have a doubt here. For upper transistor, gate is provided 5 volts and drain has given Vx,
Yes.
source is given 6 volts, no, ma'am?
This is the in-mos, na? This is in-mos.
Mm.
So here the drain is like VDD is 6 volt and the 5 volt is gate, and here the Vx, we have to find out the Vx. So what is your doubt here?
So source is given Vx.
Yes, and this is connected with this lower drain, which is connected with this gate also. Any other doubt, or is it clear, or I have to explain again?
No, ma'am, it's clear.
Okay. Just see just see the equation. It is satisfying this VDS greater than VGS or VTH minus VTH. So this is in saturation. This is also in saturation.
Okay, ma'am.
Then just took this equation, VD upper equal to VD lower. Just put the value and see the Vx is equal to 3. Then the question number 21. In a MOSFET operating in saturation region, the channel length modulation effect causes an increase in gate source capacitance, a decrease in transconductance, a decrease in unity gain bandwidth product, or a decrease in output resistance. Pradeep, what is the right answer? Am I audible?
An increase in gate source
Decrease,
capacitance.
decrease in output resistance, madam. RDS equal to 1 by lambda ID.
R0 equal to 1 by G0
Lambda ID. Lambda is channel length modulation parameter.
ID. Yes. So the right answer is a decrease in output resistance. Okay.
Yes, ma'am.
Okay. And this is the last question. For an n-channel MOSFET and its transfer curve shown in the figure, the threshold voltage is, and you can see the figure here, and the first option is 1 volt and the device is in an active region, and the second option is minus 1 volt and the device is in saturation. The third option is 1 volt and the device is in saturation region, and the fourth option is the minus 1 volt and the device is in active region. I think one more question is there, 23rd question I have selected.
Madam, option C, madam.
Yes.
0.2 times of the VDD is the threshold voltage, that is 1 volt. And again, VDS greater than VGS minus VT. That's why option C is the answer.
Yes, right, good. Option C is the right answer. This is the question number 23. Both transistor T1 and T2 in figure have a threshold voltage of 1 volt, and the device parameter K1 and K2 of T1 and T2 are 36 microampere per volt square and the 9 microampere per volt square. So respectively, and the output voltage V0 is, the first option is 1 volt, the second option is 2 volt, the option C is 3 volt, and option D is 4 volt. So we have already solved this type of problem. So please try to solve it. Again, just you have to find out the current equation for the both transistor, then you can find out the V output. Like in previous case also you have to find out the Vx, right? In that way you have to find out. So P1 is in which mode, like which region? Which equation it is satisfying? Is it satisfying this VDS greater than VGS minus VTH?
Obviously, madam. Obviously, diode connected loads.
Yes.
Both are diode connected loads.
And T2, it is also
Also,
satisfying
sir.
this equation. So both transistor is in which mode?
Saturation region.
Saturation. So ID1 equal to ID2. So tell me what is the equation for T1? How you can write?
36 into
Okay, 36
into 5 minus V naught square. No, 5 minus V naught square.
how V not VGA is like V is 5 volt. G is what
Yes.
is the value of GA is? It is V0 na. So V0 then minus VTH na. What is the value of VTH? 1 volt.
1 volt.
So can we write it like this?
Yes, ma'am.
Yes, ma'am.
Okay. And
It's
tell me
equal
what is
to
the right side equation?
9
9
into
into
V naught minus 1
1
whole
square.
square.
Oh
Ma'am, the answer is 3 volts, ma'am.
yes. So then can we square root both sides? 5 minus 1, this is 4 I think. Then V0 equal to 3 into V minus 1. So you can cancel out on this. The same V0 equal to 3. So is it clear?
Yes, ma'am.
So today up to this. We will continue our next session on next Tuesday 7 to 9 p.m. You can wait for some time. So I am going to share the link of the PPT in the chat box. Okay, just wait for
Okay,
this.
ma'am.